So let's start discussing about propagation of error, where we left it last time. And here the first thing we'll discuss is the propagation of error in summing of two numbers of same sign. The reason I'm writing same sign is because to differentiate it between, so if one is positive, one is negative, then it will be obviously like subtractions, which I want to differentiate. So that's why I say sum of two numbers of same sign. And then, so if I write it in notations, it's essentially x equals to x1 plus x2. This can be generalized to any number of x that you want, but this is what it is. So if I understand how two numbers are summation of two numbers, how the errors are propagated, you can generalize it to n number summations. Okay, just to remind you of the notations, so I will just write how this is written in terms of the exact numbers. So remember that x is a symbol, and in our notation, star gives you the number, exact number. We represent, when we say we represent the number, so that's an approximate number. So that is, we have written this with this sign. And then errors in the representation. This is error. The error is defined for these three quantities as delta x, say delta x1 and delta x2. This is error. The absolute error we wrote as delta x star with a star again. And see that this delta x star is just modulus of delta x. And then we had relative error, which we wrote with the Greek delta only. And so did we write it with a star or not? I don't remember right now. Probably did not write it with a star. So we will just keep it this way. There is only, yeah. Okay, so that will be an estimate of that, so which you can write with the estimate sign, which is a bracket of this sort. All right, and what is the definition of error? So, so this error is delta x is by definition is. So we defined it this way. You can do the, as we said, that there is a choice. You can do the opposite way, x star minus x as well. But this is how we defined it. So what we like to know first is how does that depend on, how does this delta x depends on the individual errors. So for that, what you have to do is you have to write delta x as x. Now x is nothing but, estimate of x is nothing but and then this. So what all I am doing here is writing down this x from here and extras from there. And then you subtract this or subtract this from that. So you get delta x1, that's the definition, plus delta x2. So I get delta x. The error is just the summation of the error in the individual errors in x1 and x2. Okay, but remember that when you are doing this, there is no absolute sign here, so which means that it can be either positive or negative. So keep that in mind, that delta xi, I stands for 1 or 2, can be positive or negative. Okay, So this you should keep in mind. This we will come back to later and we'll see what is the consequence. So that means that if I take modulus of delta x, which is modulus of delta x1 plus delta x2, what does this give? What is modulus of delta x by definition? What is modulus of delta x by definition?
Absolute error.
This is absolute error, delta x star, right? Now this we will agree that modulus of two numbers which can be positive or negative is always, sorry, this is lesser than equals to delta x1 plus delta x2, right? So this can be positive or negative. So because delta x1 and delta x2, they can be positive or negative. When I take the modulus, the total sum can be less than the modulus of the individuals. And then these are the individual absolute errors. So I can just write it this way. Okay. Now that's a very important result, because what does it tell you is that if I know the absolute error of the individual things, then the total absolute error is less than. So there is an upper bound in the total absolute error, which you get by adding up the absolute error of all the quantities. Okay. The upper bound on delta x star comes from summing all delta x. Now, as you can see, I have generalized it to all delta x I star, means that these individual ones, which means now if I have more than 2, if I am summing up n numbers, then also this will hold. Okay. So this is about the absolute error. Any questions so far? All right. So let's look at the relative error, because that's even more interesting. Because you see, when I am getting a number, I always want to know that what is the precision of the number. And last time, remember, we saw that delta also tells you roughly the number of significant digits, which is the precision of the number. So if I have very large amount of absolute error, then the amount of number of significant digit is actually less. Remember that if I have, if delta is like 10 to the power, delta is like 10 to the power minus n, when uh, n is the number of significant digits. So you want delta to be small. So delta is something that is important. So there is a theorem which will prove. So what does it say? It says that relative error which is calling by delta, in the sum of two approximate numbers. Let me remove this from here.
Sir,
Yeah,
so in recording we still have means
right.
screen presentation.
Thank you. Thank you. Yeah. So the relative error delta in sum of the approximate numbers is lesser than or equals to, I'm not writing in words, the largest relative error in the individuals. So if I write it in words, sorry, if I write it in notations, then delta, which is the relative error in the sum, is lesser than or equals to the largest relative error in the individuals. So maximum of delta 1 and delta 2 are the relative errors of the individuals. So this is what the theorem says. And it's not very hard to prove. So we'll do this and then we'll leave the rest of the things to you for proofing. So this is quite easy to prove. So just start with the definition of the relative error. So what is the definition? The definition is delta x star by mod of x star, right? Now, delta x star, so let's see. The denominator I can just write as x1 star plus x2 star. What about the numerator? Well, delta x star, here we have found that the delta x star is less than delta x1 star plus delta x2 star, right? So this I can write less than or equals to delta x1 star plus delta x2 star. So that implies delta must be less than equals to, you see what I want to do now is to write the delta x1 star and delta x2 stars in terms of the corresponding relative errors, and that's straightforward. I can just look at the definition of the relative error here and just do it for delta 1 and delta 2. So delta x1 star will be just x1 star times delta 1, the other will be x2 stars times delta 2. And that I can write lesser than equals to x1 star plus x2 star by x1 star plus x2 star. So what I am doing is that, so I say I don't know what is delta 1 and delta 2, but this inequality will hold if in place of delta 1 and delta 2, I write the maximum of delta 1 and delta 2, right? So that will only increase the right hand side of the inequality. So I can write this times the maximum of delta 1 and delta 2. Okay. If they are same, then you can write whatever it is. But if one is greater than the other, so you just use that, the greater number. Is this fine? Is obviously multiplied with that, the previous step.
So please explain this last step again.
Right. So what I change from the previous step to the last step is that in place of this delta 1 and delta 2, I have written something which is the maximum of delta 1 and delta 2. Okay. So why am I doing that? So because I want to bring that maximum out. And then you see the inequality still holds, because what that does is, so if I have say x1 is 1, x1 star is 1, and delta 1 is say 0.1, and the right hand side x2 is also 1, but delta is say 0.2, and then I have a division by 2, right? 1 plus 1 is 2. And I am saying that my delta is less than equals to this. This is this step. But then the next step, what I do is I say that, okay, I will just write this as 1 plus 1 by 2. But then I will replace 0.1 by 0.2 so that I can take outside common. So 0.2 is the maximum of the two deltas here. The inequality still holds because this number here, which is 0.2, is greater than this number, because I've just changed the 0.1 which was in the numerator to 0.2. Okay. So the inequality still holds. So I can write it this way. Is this fine?
Yes, sir.
Okay. So now, once that is in view, you can see what is mod of x1 star plus mod of x2 star by x1 star plus x2 star. They have the same sign, right? So what is this? Anybody? So imagine x1 and x2 are two positive numbers. So then this is 1, right? And imagine x1 and x2 to be two negative numbers. Still it is 1. So this quantity is just 1. This is just 1. Which left us to believe that delta is less than equals to maximum of. So that's the proof. Delta 1 and delta 2.
Sir,
Now this
X1
is,
star and X2 star both are positive.
they can be both a negative also, but they have the same sign.
Yes, sir, yes, sir.
Okay. So say -2, -3. Still you will have 5 in the numerator and 5 in the denominator, right? Okay. So this proves the theorem. But what is the importance of this theorem? You see, to know what is the absolute error or to estimate the absolute error, sorry, to estimate the relative error, or estimation of relative error, in summation, we can just use the relative error of the least precise term.
Sir?
Just a second. Let me make this statement clear. So this is the estimation, this is the relative error in the sum. So if I want to estimate this, I don't know exactly what it is. I just want to know a number which is greater than this. Okay. So this thing is telling you that if I know the relative error of each of the things in the sum, each of the numbers in sum, I can just pick up the relative error of that number which has the maximum relative error. Okay. That maximum relative error will contribute to the relative error of the total sum. Okay, so that is what this is showing you. Yes, go ahead.
Sir, how is this thing that you have encircled? This is one.
How is this?
This term that you have encircled.
The term,
How, am I audible? Hello?
you are not, your voice is breaking in between.
Sir, how is this term equal to 1? That mod x1
This
star
term is
plus.
1. So put in any values of x1 and x2 and check. x1 and x2 should have the same sign.
Okay, okay. So on. Oh, okay.
All
Okay,
right.
understood.
So
Yes.
otherwise it's a subtraction, right? It's not a summation.
Yes, yes, sir.
Okay. All right. So let's quickly go to the, so this is summation. So let's go to the difference and relative error in a difference. And I will use something from here. So I will use this expression because it can be readily changed for the difference case. So just we'll highlight that once. All right, so let's see what happens for a difference. So again, difference of two numbers of same sign. Otherwise, it will become summation. Okay, so this is x equals to x1 minus x2. And you can go through the same logic and see what happens to the absolute error. So you will see for the absolute error, delta x star will follow the same relation, delta x1 star plus delta x2 star. Okay, this you should check. I will not prove it for you. What about the relative error? Remember, that is what tells you what is the number of significant digits there are. Now, relative error, if I want to calculate the relative error, exactly the way we did before, the numerator will have the exact same expression. The denominator, if I go back one step, the denominator, instead of having x1 star plus x2 star, now will have x1 star minus x2 star. So that is the only difference it will have, right? So I can just use this expression with a minus sign here. Okay, so let's do that and see what happens. So x1 star into delta 1 plus x2 star into delta 2 divided by my now x1 star minus x2 star. And that is all the nuisance. So what happens is the following. What happens you see here. So remember, imagine that delta 1 and delta 2 are very small. Okay. But still delta can be very large just because x1 is almost same as x2, or x1 minus x2 is very small. If x1 and x2 are close enough, then the denominator makes delta very large. And this is a serious problem with subtraction. So this subtraction, because of this, leads to loss of accuracy or loss of significant digits. Accuracy means delta. Subtraction leads to loss of significant digits. Okay. Is this clear? We'll have an example, but before that, let me ask you if you have any doubt in this. So the way out from this is to avoid subtraction. So you write your code in such a way that you don't do much of subtractions. Okay. So let's take an example. So let's say x1 star is 1.0005 and x2 star is say 1.0004 and delta xi, both the deltas, is 0.0001. Okay, so can you tell me what is the, okay, so let me give you directly delta. It'll be easier. Okay, so this is delta I, so delta 1 equals to delta 2 equals to this. So what is the value of delta? What is delta less than or equals to? Please calculate and tell me. This is very straightforward. Yes, what it is?
2.0009.
Right. So the way I will do is, so this is 0005 plus, that is x1 star, delta I can take common, 1.0004. x1 minus x2 gives me 0.0001, and delta is also 0.0001. So this is, delta is less than equals to 2.0009. Can you tell me how many significant digits I will have? Remember that what was the way we calculate significant digits? So this is, I mean, order of magnitude estimate is this, right? So what will be n? What will be n? This term is 10 to the 0, right? So you don't have any significant digit once you do this subtraction. Okay, so that's very serious. You see that these two numbers are quite accurate. This is quite a small, so this will give you 4 significant digits, but then once you do the subtraction, you lose all 4 significant digits. Okay, so this is something to keep in mind, that you will avoid subtraction whenever you can because of this. Okay. So I will just state, I will not prove, I will just state the relative errors in product and division. Product means multiplication and division. So how do they go? So this you can verify. So delta is less than equals to now delta 1 plus delta 2. So this expression is similar to what of absolute error in the case of subtraction and addition, but now it is on the relative errors. Okay, so this just I have kept it here as a result, and then you have to remember this while doing the calculation. What we'll rather discuss is something which we can call the dancing of error. And tomorrow we'll show you an exercise which demonstrates this. I'm writing some, but this will also be true for subtraction. So one thing you remember here is that when I am talking about the way I am kind of telling about error here, I said that it's 0.0001, which will give you an error of 0.0001 here, because this is just 1, almost approximately this is just 1. So 0.0001 is your delta x star. And the way we are kind of telling these errors are these errors are, what type of error are these? These are like round of errors, right? So we are talking about round of errors here. So the definition of absolute and relative errors, etc., will all hold for any type of errors. The example we took here is for round of errors. So here, right now we are talking about round of errors only. Okay. So what happens when you are doing round of errors, or when you are adding up n terms? Okay. So the first term gives you some error. So now the first term gives you an error which is positive. And the round of error cannot be greater than half times 10 to the power something. So this is, say, half times 10 to the power some, just for the sake of example. So it's 10 to the power minus k, decimal representations, etc. So this is positive, and this is lesser than this number, lesser than this number. Then the next one says negative, next one is positive again, next one is again positive, next one is negative, negative, goes on. So what you see is that the round of errors in successive terms can be positive and negative, and in most cases, so in most cases, not in all cases, but most cases, this is random. Also, each step has a bound. So each step is bounded. What do I mean by has a bound? So it cannot exceed plus or minus this value in this particular case. Okay. So each step has a bound, and the steps are random. One error in one step does not depend on. So what do I mean by step? So what I am doing is that I have some x0, so I am adding here x1, I'm adding here x2, I'm adding here x3, etc., etc. Right? So one addition is one step, and each step the error that is creeping in is random, but the errors are bounded. So it's not each step is bounded, errors in each step is bounded. Okay. So this example is like the following example. So imagine that you got drunk and then you are asked to move. I mean, you are trying to go back home. So you take one step forward, two step backwards, then two step forward, and then one step backward, then three step forward, two step backward, completely randomly. Drunk is to become random. Okay. And then you ask the question, after n step, how much distance you have reached? Okay. So this is that problem. So this is called a random walk problem. And we'll do it computationally tomorrow as an example. But what we'll see is that the error in summation after n step goes as, it's not exactly, may not be exactly equals to, but it goes as root over of n times delta x star. So this is error after summation. This is error in each step. So this you can take as that upper bound. N is the number of steps. This is a similar expression that Einstein used to show the random walks for colloidal solutions. But anyway, so this is a very interesting result, which you'll see that will be of much interest shortly in our later discussion. Any question? Okay, so this is about round of error, right? So the other type of computational error we talked about is the truncation error. So let's ask this question, that what happens when we are asked or we are evaluating a function fx of following kind. But now numerically. Okay, so what is the function? So this is essentially given as a power series. So I equals 0 to infinity. There are infinite terms here. This is like the expression of e to the power x, if you wish. And then there is a number which is constant coefficient of the x to the power I term. So this should be I. Okay, and we have considered that. So say x is less than 1. So let's consider x is less than 1, and ai plus 1 is less than ai. The series will converge. Okay. So what if I write this down explicitly? So this is essentially a0 x to the power 0 plus a1 x to the power 1 plus a2 x square plus etc. Right? For e to the power x, it's 1 plus x square by factorial 2, etc. What we are doing to calculate this series, so we are doing two things. So one is we are summing up numbers. Right? So here we are summing up numbers. Each term in the series is a sum. What else we are doing? Remember, we cannot do the infinite sum, so we have to stop somewhere. So we have to truncate the series. So truncate the series means instead of evaluating this, I will evaluate it up to I goes from 0 to a finite n, right? Finite number of steps. So we need to truncate the series to some n. What will this give me? This will give me round of errors, which we have just discussed. And this, as we have just seen, depends on root over of n into delta xi. This is what we have just seen in the previous page, root over of n into delta x. Okay, delta xi, I just written I is for one step. You may forget the I, and then there is a star, doesn't matter. This will give you truncation error, right? Now, how does the truncation error supposed to behave? How does it supposed to change if n is made larger and larger? Do you think that, so round of error increases as root n, right? So as n increases, the round of error keeps on increasing. What do you think will happen to the truncation error? What do you think will happen if I keep the first term compared to 2 terms, compared to 3 terms, compared to 4 terms?
Sir, it will keep decreasing.
It is supposed to decrease, right? So as you keep more and more terms, the truncation error is supposed to decrease. Now, so I will not
Sir,
prove it. Yeah, go ahead.
so but like on the other hand, if we also see that x square and powers are there, right? So the error will become that much multiple of the power. Uh, so in that way, it can increase also, right?
No, so that we have already considered in round of errors.
Okay,
Right?
so it's
So,
same.
so what you mean is that this delta xi may be not exactly the error in 1x, but it can be a little more convoluted things, right?
Yes, sir.
But now, yes, you are saying that okay, so I will not use up to after the third term, so I get some error. Compared to, I will not use after the sixth term, so I will get a different amount of error. The sixth term case, my error is less, as the series is convergent. So this depends then on what series you are evaluating. Okay, so this depends on actual series evaluation. In general, this goes as some alpha by n to the power beta. So it's a power law in beta. Sorry, power law in n alpha and beta both greater than 0, so you see that decreases as n increases. But how fast or how slow, that will depend on the particular problem. And this is something that you will learn when you will learn different algorithms. So then you will see that this is something that you learn for each algorithm. How much is this? So this tells us that the total error, if I write that, say, delta x, in this summing the series, is root over of n into delta xi star plus alpha by n to the power beta. And it is always useful to have a picture which gives us more understanding. So let me draw a picture for you. So x-axis I am plotting n, and y-axis I am plotting. So let's first plot root over of n time delta x I star. How will this look? This will look something like this, right? It's also useful to plot the same thing in a little different way, which is called a log-log plot. So I have just taken log of this and the log of this. How will it look in this plot? If I take log of both of these,
It's a straight line.
it will look as a straight line. If you take the log of this, it will become a straight line. So it will be some straight line here. On the other hand, if I plot alpha by n to the power beta, so that is something that decreases with n. So it looks like this here and looks like this here. Exactly how it will look, again, obviously will depend on the exact values of alpha, beta, etc., etc. So when you have the combined thing, the total error in this case looks like this. It's this. Right? I just say add these two terms. Obviously, everything is run by hand, so it's not exact. What you notice is that there is an optimum value of n. Right? See, truncation error, because it may seem for us that if I keep more and more terms in this series, what will happen is that I will get a better expression for fx. Okay. Or looking at just the round-off error, you may say, okay, I will keep less terms in series, then the round-off error will be less, I will get a better expression, which is obviously not correct. Obviously not correct because the first term, if you add the second term, mostly it will be better than the first term, only the first term. But you see that neither of these are correct. You have to find out that optimal n, and if you change the n in the other way, the error will increase. Okay. So now, after doing all this mumbo jumbo of error analysis and so on, we have learned something very useful, that given a calculation, if I want to do it most precisely, what I should find out is this optimum n up to which I will series that sum or sum that series. Okay. Any question? Is it that all these were already known to you?
Sir?
Is it that all these were already known to you?
Sir, what is this white curve that you have drawn?
This curve?
Yes, sir.
This is the total error. Adding these
Oh,
two.
okay, okay.
Okay, so it follows this here and then the other one. Okay, so what I will do now in the rest 5-6 minutes, I'll just introduce you to the representation of numbers. You see, it is important. Why it is important? Because the precision that we were talking about depends on the representation of the number. The precision is sitting here, which means when you are trying to figure out that what is n optimal, it depends on this number here. So that depends on how the numbers are represented in a computer, and that is what we'll talk about the rest of the today and mostly in the next class. Okay, and there is a lot of things that one can talk about in representation of the numbers. Obviously, we will concentrate or restrict ourselves to a very brief one. Okay, so why do I need to have a representation of the number? So there are two very important points here. One is that the computer has a finite memory. So I cannot have an infinite precision number in a computer. So I will always have a finite precision number. So I cannot represent the number pi exactly in the computer because I can only have finite precisions. The other interesting thing is that the computers, the modern day computers, digital computers, they uses the main device in that is a switch. The switch has two states. So this is a device, which is a transistor, of course. It has two states, on and off. So if you want to represent a number, the most favorable number base is the binary. Okay. Now there are very simple definitions, which probably you already know. So one binary memory place. So one place in memory is called a bit. So this is like one transistor which is either on or off. So I will represent it like this, which is a box. In that box, you can have either the number 0 or the number 1. Okay. And then you collect certain number of these boxes and you call it a byte. Byte is 8 consecutive places in a memory. So you have 8 of these. So you can have 8 combinations of zeros and 1. So this is written with a capital B and bit is written with a small b. Okay. So many times you will be fooled by saying that you have a connection which is 1000 Mbps. Okay. That B is small b, that means that is 1000 megabits per second. If that B is capital B, it means 1000 megabytes per second. So you get a 1000 megabits per second connection, and then you start to wonder that why my download speed is so slow. It's because there is a factor of 8. So always look at in your download speed whether it is small b or capital B. Okay. So now the one representation that we'll glimpse on today is the integers, which is easier to represent. Okay, I'll not go very further because the time has almost come to an end. But let me pose a question and then we'll discuss on that and finish. So a number, an integer number, what is the problem? What can be the problem with integer representation in a computer? Remember that you have a finite precision, which means any representation has a finite number of bits or bytes. Okay, so now tell me, what do you think can be the problem with integer representation? And we'll complete at that note.
So decimals cannot be exactly represented.
No, I just want to do all arithmetic with integers only.
Okay.
What can be the problem then?
Sir, there will be an upper limit to the integers represented by the
There should be
computer.
an upper limit to the integers, and if you have the integer with a sign, then there will be a lower limit to the integers as well.
Yes, sir.
Right? There is no upper. So what is the maximum integer? Can anybody tell? There is no maximum or minimum integer, right? But when you represent that in a computer, you have a maximum and a minimum integer. So what the computer end up doing in integer arithmetics, like multiplication, division, not division, multiplication, subtraction, and addition, is called a modulo operation. So before you come next time, modulo. Check what is this modulo addition. And then we'll take it from there. If you know already, then it's fine. Otherwise, you can check. Any question? Please raise.
Sir, at what time we need to log in tomorrow?
Tomorrow's class will start at 3 instead of 3:30 or 2:30.
Okay, sir.
Any other question? Otherwise, you can leave. Okay, all right. So see you tomorrow in the lab class.